All right, so this last bit out of chapter 17 is relatively straightforward. It's just one more application. It's completely different. We're not talking about batteries anymore. We're talking more about kind of electrical energy and kind of some of the things that we can do with this information. So I just wanted to take a quick second here and look at just a couple of key units associated with electricity and systematically define these three terms in terms of the units that they have. So when we talk about current is the amount of charge delivered over a period of time. And the standard unit for current is the ampere or the amp. It's given by a capital A. An amp is simply a coulomb delivered every second. So if I have a 1 amp current, that means that that current is delivering 1 coulomb of charge every second. In terms of work we usually associate that as an energetic term. We've already talked about that. That's joules. Joules being the combination of coulombs and volts. And power is a measurement of capacity of energy. And so what we usually use there is the watt. And a watt is a joule delivered every second. And if you put kind of the terms all together here, you can see that if I substitute this definition of coulombs in for amp or using amps and seconds, I get that joules are an amp times seconds times volts. Well, if I do that same thing here with power, a watt is a joule per second. Well, joule is amps times seconds times volts. So if I combine them, seconds and would cancel out. We can also talk about this in terms of its amps times volts if I wanted to get into a discussion of power that way. So one of the reasons we bring this up is because thus far, all we've really ever talked about was the voltaic cell. That is the cell that is created that gives us electrical energy spontaneously. And every battery that we've made has that kind of thing in common. Even if it goes the opposite direction that we wanted it to, that it still was producing electricity. It was just going a different direction. And I can't believe how wrong that is. You have to give me a second here. The slide has it completely backwards. Let me So that's going to take a second because it has to resync, and it'll probably put all the slides out of order again. But it was completely backwards. And yeah, that's bad on me for not fact checking the book slides before I posted them. All right, so if they show up a little bit out of order, we'll just kind of deal with it. All right, so we've done all this with voltaic cells. They're spontaneous reactions, and because they're spontaneous reactions, our E cell value is always positive in those cases. Electrolytic cells are the exact opposite. What we're doing is we are forcing a bad reaction to happen by basically supplying it with an excess of electrical energy. So we did an example of this yesterday in the lab. We hooked up that YouTube to the power source, and we got iodine to form from iodide when it wasn't supposed to. We got water to split into hydrogen when it didn't want to either. So those E cell values that are associated with electrolysis, they're always going to be negative because the spontaneous process is not happening. The non-spontaneous process is being forced instead. And that does make a difference. That does make things kind of unique. But what it does show is that there is a distinct difference. I can have a voltaic cell that generates its own electricity, and that electricity can be used to power things like light bulbs or buzzers or switches or electronic devices, telephones, laptops, you name it. But I can take that same chemical reaction, hook it up to a power source, and drive it the other way if I wanted to, if there was some reason to. And one of the reasons you might do something like that is to do this process called electroplating. Electroplating is probably the most common process we have for doing electrolysis, because what we are doing is we are basically running electricity through a series of wires to force the reaction to go the wrong way. And the result of that reaction going the wrong way is the depositing of metal onto the surfaces of other things, usually other metals. So this is the process by which we get things like silver plating or gold plating taking place, where you can take a piece of jewelry, hook it up to a solution of gold, and run the reaction backwards and get that gold to deposit on top of the cheaper metal that it's made out of. You know, this process is used in a lot of different kinds of processes. So, for example, if you want to have a trophy or a statue like the Oscar there, you don't want to make that whole thing out of solid gold. Costs way too much money. But having a gold veneer on it, well, yeah, you could do that. Electroplating can be an easy way to do it so that you get an even covering, as opposed to using gold foil or leaf, where you'd have to have someone bang that out to get it smooth enough to work. And the process that is usually used there is the formation from cyanocomplexes of gold, which introduces other kinds of fun chemistry as well, because you're dealing with cyanide complexes in solution. Now, some of those definitions that we needed to use, that we needed to quantify at the beginning here, really come into play when we try to quantify what exactly we need to do as far as current is concerned, or if we're trying to deposit a certain amount of our gold or our chromium or whatever it is to our metal. And so the process that we go through is kind of this linear process where we need to know our current and our time. So that's the top window here. Or we need to know how much stuff we're going to deposit. And we can connect all of those dots through these other processes. To do this, we need to know something about the half reaction. So we need to have a quantity to look at, in particular, a mole-to-mole ratio. We need to know how many electrons are being exchanged. So that would be our value of N. We need to know the measurement of current. And if we don't know the measurement of current, then we at least need to know how long the thing is going to run so that we can figure out what current to run it at. And so what this process is going to look like is really just a series of steps that kind of resemble unit conversion. Because these individual steps are really just kind of a series of equations. Current times time, so amps times seconds, would give you the quantity of charge Q. And we'll moles of electrons to quantity of charge. Well, that's the Faraday constant. Moles of substance oxidized or reduced to moles of electrons. Well, we get that from the balanced equation. Grams to moles, molar mass. So all four of these types of conversion calculations are relatively straightforward. The only one that's really not in that realm of conversion using dimensional analysis is that first one. But even it could be if we happen to be going the right direction along the way. So let's take a look at an example. Calculate the mass of aluminum produced in 1 hour by the electrolysis of molten aluminum chloride if the electrical current is 10 amps. Now, based on what happened yesterday, can we answer the question why we're doing this in molten aluminum chloride instead of aluminum chloride solution? the reduction potential of aluminum is more negative than the reduction potential of water. So if I did this in solution, all I'd get was a bunch of hydrogen instead of the aluminum. So it has to be done in aluminum chloride because of that competing reaction with water. So anyway, the reduction potential is not actually relevant here, but what is relevant is the equation that we would use to find that reduction potential. That is the half reaction. In this half reaction, we see that this is a 3-electron process. So N is going to equal 3 when all is said and done here. Now, the way to approach this is looking at it kind of from what can I convert to next kind of standpoint. So I know I have amps here. Amps are coulombs per second. If I have 1 hour, hour's a unit of time. If I convert that hour to seconds, I can use the current to convert the seconds into coulombs. So that's what I'm going to do. 1 hour is where I'm going to start. Every hour has 3,600 seconds in it. 60 times 60. And according to the current, in every second, I will get 10.0 coulombs of charge. So if I stop the calculation right here, this would tell me the amount of charge generated by this electrical source in that 1 hour. Now, that particular information isn't super relevant to me right now, but I can make it relevant because I can look at this and say, okay, hours have canceled, seconds have canceled. I've got coulombs. Is there anything that I know about coulombs that can relate to this balanced equation? And that's where the Faraday constant comes in. Faraday constant says 96,485 coulombs is equal to 1 mole of electrons. So my coulombs cancel. Now I've got moles of electrons. My balanced equation here says that for every 3 moles of electrons, I get 1 mole of aluminum. And now I know how to do the rest of it. 1 mole of aluminum is 26.98 grams according to the periodic table. Yeah. So moles of electrons canceled, moles of aluminum canceled. All that's left is the grams. So I just need to do all of this multiplying. This is kind of fun to think we're coming full circle here. We started way back in Chem 105 talking about dimensional analysis. And what's the very last concept that we are doing in Chem 106? Well, it's an application of dimensional analysis. We have closed the loop. All that's left is we're going to talk a little bit about solid state on Monday. Really, that stuff's probably not going to show up very much on the final. We've got a quiz on it. We've got to satisfy certain content standards for the state. That's why we're doing it. But really, this is it. This is our last concept. So we put this all together. 1 times 3,600 times 10 times 26.98 divided by 96,485 divided by 3. So that 1 hour of current yields us 3.36 grams of aluminum. which doesn't seem like all that much. And it really isn't. That's also, that's kind of the nature of plating. We usually don't need that much to do what we want to do. We're just trying to create a thin coating on the surface of the metal to improve its appearance or to make it a little bit more corrosion resistant or, whatever the case may be. Right. Any questions with this example? All right, here's a different kind of application. It's the same relative idea, but a different application. We're going to recharge a AA battery. In the recharging of that battery, we are going to convert nickel hydroxide to nickel oxide hydroxide. So in that process, we're going from a nickel in the +2 state to a nickel in the +3 state. How do I know that? Well, hydroxides are -1 each, so that's why the nickel's +2 there. And if I look at it here, I've still got a -1 hydroxide, but now I have a -2 oxide on it. So that's a total charge of -3, which means the nickel has to be +3 as a result. So the process here is slightly different, but in a lot of ways the same. The equation here is as follows. So that's the oxidation that's taking place. We're going to start with our 0.649 grams of nickel hydroxide. And the first thing that we're going to do is like we would do for any equilibrium problem, frankly. We're going to turn that grams into moles. We just got to look up the molar mass. Molar mass of nickel is 58.69 plus 2 oxygen, so 2 times 16, plus 2 hydrogens, to 2 times 1.01. We get 92.71 grams in every mole. Now we can go to the balanced equation. 1 mole of the nickel hydroxide is going to yield 1 mole of electrons. Every mole of electrons is going to require 96,485 coulombs of charge. And we've got a current of 1 amp. So that means 1 coulomb is going to be generated every second. So 0.649 times 96,485 divided by 92.71. And so it will take 675 seconds to oxidize this process. It did ask us for minutes, so we do need to do one last conversion, 60 seconds in 1 minute. So this would be 11.3 minutes to do this conversion at that current. So it's not electroplating, but the process for solving this electrolysis problem is effectively the same. We're just going through and kind of doing the stoichiometry, getting ourselves to moles of electrons, and then applying our electrical definitions to that number of moles of electrons to figure out charge, to figure out time. So it's kind of the reverse of that first problem that we did. All right, any questions with this? All right, so I want you to try one before we put this one away. We've got a chromium-3 solution being electrolyzed using a 7.6 amp current. We want to determine the mass of chromium to be plated out after 2 days. So that's the first problem. And then the second problem is what is the mass, or excuse me, what is the current that we would need if we were going to plate out a 1/4 mole of chromium from solution in a period of 8 hours? So 2 different problems, but they should be solved in relatively the same kind of manner, at least with the same calculation technique. So go ahead and chew on those, and we'll come back in a few minutes and talk about it, see how we did. All right, let's take a look and see how we did. So for the first one here, first one plays out very similarly to what we did in the first example problem. We have a time, 2 days, and we have a current, 7.6 amps. We need to convert that into a mass. So that's kind of what we're going to need. That's kind of what we're going to do. We're going to take the 2 days. Okay. Every day's got 24 hours in it. Every hour has 3,600 seconds in it. And now we start to apply the electrical data. Every second gives us 7.60 coulombs. There are 96,485 coulombs in every mole of electrons. And since we're going from chromium 3 to chromium, the balanced equation there three moles of electrons for every 1 mole of chromium. And every mole of chromium weighs 52 grams. So if I carry it through all of the way, two times 24 times 3,600 times 7.6 times 52 divided by 96,485 divided by 3. To 3 significant figures, it's 236 grams of chromium. So that better be one big hubcap. Now, considering 2 days of chroming on it, yeah, that's a lot of chromium. It makes you wonder what the solution was that it came from in the first place. So that's the first one. For the second one, this one's going to require a little bit more thought because we're basically solving for an interior step. We need to know separately the number of coulombs that are going to be required and the amount of time. That's how we're going to get amps. So amps are equal to coulombs over seconds. So what we really need are a pair of calculations that give us coulombs and seconds separately. Well, the seconds part's kind of easy. 8 hours at 3,600 seconds per hour, 8 times 3,600 gives me 28,800 seconds. That one's easy. For the coulombs, that's where I'm going to have to do a little bit more thinking. And where I need to be thinking is in this part of the reaction, where I'm going to take my moles of chromium, turn them into moles of electrons, turn the moles of electrons into coulombs. So I've got a 1/4 mole that I'm trying to make. Balanced equation says that for every mole of chromium, I would get 3, or I would need 3 moles of electrons. And each mole of electrons, according to Faraday's constant, is 96,485 coulombs. So 0.250 times 3 times 96,485. To 3 significant figures, 72,400 coulombs of current, or of charge rather. So to find the current, to find the charge per unit time, 72,400 divided by 28,800 to 3 significant figures would be a 2.51 amp current. So ultimately, that's what we would be looking at here, is we'd be looking at that as our current. Any questions about electrolysis? All right, so that is it for this chapter. Go ahead and hit the stoplight question, and we will call it a day for that.